Professor Warren Gross received a BSc degree in electrical engineering from the University of Waterloo, Canada in 1996, and MSc and PhD degrees from University of Toronto, respectively in 1999 and 2003. He is currently a James McGill Professor and the Chair of the Department of Electrical and Computer Engineering, McGill University, Montreal, Canada. His research interests are in the design and implementation of signal processing systems and custom computer architectures. Dr. Gross is a licensed professional engineer in the province of Ontario. He served as chair of the IEEE Signal Processing Society Technical Committee on Design and Implementation of Signal Processing Systems. He has served as general co-chair of IEEE NanoArc 2021, IEEE Global SIP 2017, IEEE SIPS 2017, and as a technical program co-chair of SIPS 2012. He served as an associate editor of the IEEE Transaction on Signal Processing and as a senior area editor. So, Professor Gross, the floor is yours. Thanks. Please start.
Thank you very much, Danilo, for the introduction, and I'm glad to be here with you all today to talk about on-device learning. And my talk today will focus on on-device learning for natural language processing, NLP, using a class of models derived from what we call the BERT model. So here, I'm going to start with a definition of on-device learning. It's actually the one that Danilo read out this morning. It's not my own. It's one that I like. It's from tinyML. And so I'll just review it briefly now. The goal of on-device learning is to make edge devices smarter and more efficient by observing changes in the data collected and self-adjusting or reconfiguring the device's operating model. Optionally, the knowledge gained by the device is shared with other deployed devices. So what we're focusing on in our lab is edge intelligence broadly, so bringing AI and machine learning to resource-constrained edge devices. And in particular, we're very interested in on-device learning. So why are we pursuing this? And I think the other speakers had some good introduction to this topic. The idea is being that all your data is curated and processed entirely on the device. So a couple of very compelling reasons for this. First of all, if you do this and you keep your data only on the device and don't send it to the cloud, then cybersecurity and privacy are built right in. There may be commercial concerns or regulatory concerns that prevent you from sending data to the cloud. The other good motivation for this edge intelligence paradigm is quick adaptability to environment. There may be applications, for example, self-driving cars, where you would like to avoid the latency required to communicate with the cloud. You need to make decisions quickly on device. As well, there may be applications where the power required to frequently communicate with the cloud is prohibitive, and therefore meaning that the processing should happen on the device. And so this is the framework in which we're operating. So I wanted to give you just a brief overview of what we mean by natural language processing. So the idea of NLP is to have a machine gain some sort of understanding of human language. And there's many different tasks under the umbrella of natural language processing. What I've shown here is just a small sample of the kinds of tasks that fall under this umbrella. So on the left, you can see there's a task called question answering. So if you have some text, then you should be able to ask the machine questions about the text and get answers. There's an example given here of named entity recognition. So in this sentence, we're able to classify Jim as a person, Acme Corp is an organization, and 2006 is a time. There's also multi-genre natural language inference, where you have a hypothesis and you want to check whether a given sentence relates to the hypothesis or is unrelated or contradicts it, and what have you. So these are the kinds of tasks that we're considering. Now, how is natural language processing done? The kinds of neural network models that we use in NLP are generally quite large. Lots of layers, many parameters, many weights. And in fact, there are many different applications as well. So you need to have many different models trained by many different data sets. So that's not typically exactly how it's done. What is done in particular, most of the time, is you have a huge data set to model a language, and you do some kind of training on this huge data set, which is not going to be very useful for a particular task, but this takes a very long time. Once you have that, we call that a kind of a pre-training, then we can fine-tune that resulting model for specific tasks and using some task-specific custom data set. Okay, so fine-tuning is what we're going to be referring to in this talk. Refers to the procedure of retraining a pre-trained language model using some task-specific, custom data. So on the left, you can see there's a neural network. This is pre-trained. And when we talk about fine-tuning, usually what we mean is just retraining on some smaller data set that will, and you only really modify the last layer or two in most cases. You're not retraining all the layers, just the last couple of layers, or even just the last layer. So the goal of our work in general is to do everything on a single device, to do inference and training on a single device, to move the inference from typically GPUs, NPUs, or tinyML CPUs onto the device, and as well to take training, which is almost always done with GPUs or NPUs, onto the same device. Okay. Now, when we talked about NLP, we mentioned there was a pre-training phase. This is not something that we are aiming to do on the mobile device. To give you an idea of how much compute you need for pre-training, to pre-train a model called BERT-base, using 64 server class GPUs requires usually thousands of dollars to do this pre-training, up to $12,000, and it has a very significant, actually non-negligible environmental impact as well. So in this talk, I'll overview some of the work we've done about doing the fine-tuning step to adapt NLP models to various tasks on mobile devices, and we're targeting mobile GPUs. So this is not something that we are looking at yet to do on mobile CPUs, but on mobile GPUs there actually still are a number of challenges, and so I'll give you an overview of what the challenges that we encountered were and some of the ways that we mitigated those. And it really comes down to give you sort of the punchline, to figure out how to optimize memory management to decrease the time for fine-tuning on mobile GPUs without ideally affecting the inference time too much, or the accuracy of the language model. The goal being now reduced training time and higher energy efficiency. Okay, so I'll give you a very brief introduction to the kinds of models we're training. These are called BERT, or bidirectional encoder representations from transformers. And if you look on the right, you see a little diagram of BERT. It has three general parts to it: an embedding, then encoders, which are these self-attention heads, and then a classifier. So if we look into the encoders, what we see is they're usually implemented with fully connected neural networks. And most of the weights in the model are actually contained in these fully connected layers. And there's a lot of ways. These are very large models. So the base BERT model you see in the table, the top line, has 109 million parameters. When you run this model to do an inference on a Pixel 3 smartphone, an inference takes 1.7 seconds. So you can see this is quite a significantly sized model. Now there are a number of compressed versions of BERT. I've shown a couple here, mobile BERT and SqueezeBERT, and they're actually very successful at reducing the number of parameters significantly. So mobile BERT has, a quarter of the parameters, and SqueezeBERT has about a half, and this results in inference speedups on the order of 3 to 4 times, which is significant. Meanwhile, maintaining competitive accuracy as measured by the glue score. So they do it different ways. They both compress the model. In particular, and we'll look at SqueezeBERT in a little bit more detail later in the talk, the way it does it is it approximates those large fully connected layers in BERT base with something called grouped 1D convolutions. And it's good at compressing, but there are some issues that come up when mapping this to mobile GPUs, which we'll go over. Okay. So the takeaway you should have for the first part of the talk is that training BERT is very slow. Of course, there is this pre-training, which is done in the cloud on a large unlabeled data set of simple language tasks. And then there's the fine-tuning, which is what we're aiming to do on the mobile GPUs on small task-specific data sets for the different kinds of tasks, like MNLI or NER or SQuAD. Okay. Now, I direct you to the graph on the right side of this slide, which talks about fine-tuning time. So the amount of time it takes to do fine-tuning on a particular task, about semantic textual similarity. And first we'll look at the blue curves, which are the training times for BERT base and also SqueezeBERT on a server class GPU. And as you could expect, the compressed SqueezeBERT trains faster. It fine-tunes faster than the base. So that's as we think. It has many fewer parameters. But perhaps counterintuitively, as shown in the red curves, the training time for SqueezeBERT is in fact longer than the training time for base when you do it on a mobile GPU. So we asked ourselves, well, why? Why is this the case? We found a couple of interesting things. First, that this slowdown is task agnostic, so it's not just specific to this task. And second of all, the reason this happens is because of just a particular memory access pattern that occurs when you implement those encoder layers with 1D group convolutions. And we'll go over those a little bit as to describe what that pattern is and how we can mitigate it. But it's essentially a memory access problem, which doesn't map well to the mobile GPUs. Okay, so we'll look now at I think 3 different approaches to dealing with doing the fine tuning on mobile GPUs. The first we call freeze and reconfigure. And so we started by looking at compressed models. There's another one called distill BERT. And one of the things that we found is that when you compress the model, you actually increase the time it takes to converge to a good accuracy. They require extra fine tuning to reach the same level of performance that the uncompressed model has. And so one of the things that you see people do in these models to generate them is they do very aggressive weight freezing. And this is responsible for large drops in accuracy in these compressed models. So we looked at a couple of techniques to try to address this accuracy drop, and really are trying to aim at a trade-off, a good trade-off between accuracy and compression. So the first thing we tried is something called freeze and reconfigure. So there's 2 steps to this. We're going to, in the freeze step, try to identify nodes in the feed-forward layers where the learning is happening in good part, and conversely, other nodes where there's not much effect during the learning process. And the idea being, well, let's freeze what we call the non-learner nodes and don't update them during the backpropagation, and this should result in a speed up. And then the second step, once we've frozen, is to take the learner nodes that we're actually going to update during backprop and reconfigure them into a contiguous allocation so that we can take advantage of structured memory accesses instead of sparse memory accesses. So how do we figure out, first of all, which are the learner nodes and which are the non-learner nodes or frozen nodes? So we call this step priming. What we do is we look at the optimization steps, which consist of a forward pass, a gradient update, and a backward pass for one mini batch. And we run some percentage of those initially, percentage P, that's called the priming percentage. And this is typically a very low percentage, for example, 1% of all the steps. And what we do is we look now at the weights that we got at the end of these priming steps, and we take the difference between those weights and the pre-trained weights, and we calculate the L1 norm. And we use that to threshold which will be the learner nodes and which will be the non-learner nodes. And so there's a couple of knobs you can turn here to look at the trade-offs between complexity and performance. The priming percentage P, turns out that you don't get much benefit in most cases from doing that beyond 1%. So in this talk, we're going to fix that at 1%. And then you have this other percentage, the retention percentage, which is how a percentage of nodes do you retain. And so that's something that we're going to look at the effect of between 10 and 40% usually. So the next step, once you've identified learner nodes and non-learner nodes, is to group them into contiguous areas. So, for example, here in the regular networks, you have some learner nodes in green and non-learner nodes in red. We've identified those. Now we're going to group the learner nodes into one group and the non-learner nodes into another group. And the reason why we do this is because it's an implementation thing. In PyTorch, we can use automatic gradient computation if we have the nodes grouped. We can't disable computation for an individual node or parameter, but we can for whole layers or sublayers. So if we group into sublayers, we can use the automatic gradient computation. So there's no extra implementation complexity here. It's something that we can just do automatically. That's actually not completely true. There is some, because once we've grouped them, we need to ungroup them by doing a permutation. So there is some overhead in doing this, but this is what enables us to do dense instead of sparse memory accesses. Okay, so here's the performance on a number of selected tasks normalized to the baseline. So the baseline is 100 here in terms of metric performance. And we looked at freeze and reconfigure for retention percentages of 10% and 40%. And what we can see is across these tasks, there's not a lot of loss. Obviously, the higher that percentage is, so 40% has better performance than 10%. So it's really a trade-off, but you get most of the performance of the baseline. You can even notice on one of these tasks, SST2, that in fact we outperform the baseline. And that's actually not unusual in that this is probably acting as a regularization. So it is possible to do slightly better than the baseline in some selected tasks. Okay, so overall, how does this, what does it buy us? Well, if you look at, compared to not using the technique at all, so a retention percent of 100%, we looked at the wall clock time to do the fine tuning. And as you retain fewer and fewer nodes and update those, you see a reduction in fine tuning time. So we can get up to 30% reduction in fine tuning time, depending on the trade-off. So I'd say between 20 and 30% is the realistic range of values. And looking at the contribution from this, we found that a huge part of the contribution is actually in access to main memory. That's been reduced because of this freeze and reconfigure. Okay, so that was a first attempt, and then we wanted to improve it and further improve the trade-off between complexity and performance. And so we looked at some techniques which we call learning modules. And so there's a number of techniques that turn off weight updates during learning. So for example, BitFit, you can see it's B here. It takes linear layers and it just freezes the weights during learning, and it only updates the biases. And so there's a number of related techniques, for example, adapters, which add actually additional linear layers into the model, which are trained. These are smaller, so they kind of are able to take the role of the frozen modules in gray and learn a smaller representation of them. The difference between learners and adapters is that these learner layers here are actually then folded into the linear weights for inference. So we don't have, these are only there for learning. They don't really hang around for inference. And we can see the effect of these if we look at the convergence time, the number of epochs it takes to maintain a particular training loss. And we see some of these techniques, while very, very effective at compression, like BitFit or adapters, converge very slowly. So what we're really trying to obtain here is a trade-off between convergence time and memory compression. So here are the results. Okay, so the baseline has 67 million trained parameters and takes about an hour to train. You can see it uses a large amount of 1.3 gigabytes. Okay. Now, if we look at adapters, some prior art, they're very, very effective in reducing the number of trained parameters to 5 million and cuts the training time in half. And you can see that the memory allocated also is substantially reduced, but there's a large reduction in glue score. So our first attempt I showed you was the freeze and reconfigure. It somewhat reduces the parameters, but not that much. And again, with a corresponding interesting but not very huge reduction in training time, but it has good performance. So the learners are a good trade-off between these here. Again, we receive a very significant compression on the same order as adapters. You lose a little bit of advantage in training time, but it's still pretty significant. And you can see that the glue score is comparable with the baseline. So it's a really good trade-off, we believe. I want to talk about one more short topic, and this has to do specifically with fine-tuning SqueezeBERT. And SqueezeBERT is that model that replaces fully connected layers with 1D convolutions, which are mathematically equivalent. What SqueezeBERT does, however, is it makes an approximation to the 1D convolutions called 1D grouped convolutions. It breaks things into groups. And when you do that, you can actually reduce the number of parameters by a factor of 1 over g if you have g groups. Okay. The problem is that we found that when you do this, it trains really slowly, fine-tunes very slowly on mobile GPUs. And the reason is a couple of reasons. Let's look at this graph and let's focus only on the dashed lines for now. And you can see that this shows you on the right, it's the L2 cache miss rate on the GPU. And it's very, very high for SqueezeBERT, much higher than it is for BERT-based. So the first takeaway is that there's suboptimal cache performance on SqueezeBERT. And second of all, there's a lot of off-chip memory accesses. This is actually the bar graphs. It's higher for SqueezeBERT than it is for BERT-based. And this is due to inefficient low-level allocation in CUDA, because when you do the group convolutions, even though you're saving parameters, you still have to allocate the memory for the whole layer, even though you're not only updating a part of it. A note about that, actually, I wanted to give you a note about that. That's an implementation issue, which has, I believe, been solved in TensorFlow Lite, but this is not applicable to what we're doing here. So it was an issue for us. So, okay, so the results, what we did was, instead of using the grouped 1D convolution, we actually went back to using fully connected layers, but in the grouped manner. So we have a number of parallel small fully connected layers, which we concatenate together. and this helps us mitigate the memory access problems. So the takeaway here is we received a 20% reduction in off-chip accesses and a 15% reduction in L2 cache misses. Overall, this resulted in a 42% reduction in fine-tuning time on average. There is a trade-off here. By modifying the model, we do experience about 5% penalty on inference, but no effect on accuracy. The accuracy here is we're computing exactly the same thing, just doing it in a slightly different memory access pattern. And when we studied this to see where the contribution and the training time was coming from, a large amount is from the main memory optimizations that we did. So I think I'm coming up on my time here. In conclusion, training large NLP models on edge devices is challenging because of the very large size of the models, and in particular, the very inefficient memory layout of BERT models. So we've examined this and proposed a technique for reducing the number of parameters trained during the on-device fine-tuning of compressed BERT models that have very low performance loss. And we've also looked at the memory access patterns for SqueezeBERT in particular and found that there were some specific issues when training it on mobile GPUs. And also we looked at ways to optimize those patterns with no performance loss, with a slight loss in inference efficiency. So with that, I'll stop and invite questions. Thank you so much.
Thank you so much, Professor Gross, for your very interesting presentation and to have elaborated the NLP subject with regard to on-device learning. There is one question. In this presentation, high-end embedded machine learning hardware were used like Jetson. Are there experiments done with microcontrollers for BERT?
Oh, that's a great question. As far as I can tell, and I could be wrong, I don't know if I have the exhaustive list of things in my mind here, but this is, to me, at this point, really hard to do on microcontrollers, and it's not something that we've looked at this point. I'm really curious to see if we could, but I think that'd be optimistic right now to do this on a microcontroller.
Thank you. And also, I have a few questions from my side. So you elaborated the group group learning. You elaborated how to group learners in order to improve the efficiency of the memory accesses. Do you think that this technique is agnostic if quantization is used?
Oh, I would say I wouldn't know the answer to that, but that's a very, very good question. Is it agnostic? I think that's a very excellent question. I think we would demand further investigation, but
thank you. Thank you.
And,
sorry, I didn't want to embarrass you, but you know, also I was curious on how to see if BERT can be really deployed on tiny devices for some cases, and this I understand is still a challenge. I was wondering if you have any thought on another aspect related to BERT models. Now, there is, at least for what I know, one deep learning framework that offered recurrent layers in a quantized way. Quantized means also deeply quantized with the number of bits to express integer number. So do you see that, first of all, is still prohibitive try to quantize BERT or to develop, let's say, memory tiny memory models for BERT, so is subject of research, or do you see opportunity in that way, in that let's say in that respect, or is it a dead end?
Oh, I wouldn't call it a dead end. I do see that there still needs to be a lot of research done there. For example, we saw that just pruning weights, not even looking at quantization, but that actually results in a significant reduction in convergence. It makes it long. It takes it longer. So the problem is, you know, when you have these large over-parameterized models, it's very easy to do stuff. But when you start now working with these very highly compressed models, again, I don't want to give an answer that's not correct. So I'll just say that this definitely is a result of future work. And I can see there's actually a comment in the Q&A, which actually makes oh, sorry, this is not a general reference, so perhaps it's not referring to my question. I thought it was a real-time answer to my question, so we'll leave it at that. Thanks.
Okay, thanks a lot, Professor Gross. It was really a pleasure to have you with us today. Please stay with us. Thanks, the strategic partners, once again, because without them, these type of forum and many other initiatives would be impossible to organize. And the strategic partners are ARM, very quickly, Edge Impulse, Qualcomm. Then we have the Platinum strategic partner, DeepLight, Clicatech, Reality AI, Renesas, Sony Semiconductor, the Gold strategic partner, Analog Devices, PhotoHub, Microsoft, NXP, Seed Studio, Sensimil, ST Micro, Synaptics, ScienceSense, and then a bunch of silver strategic partners, which are listed here. Thanks a lot. It was really a great afternoon for me, and whatever is your time zone. Thanks a lot. No words to express gratitude to the professors and all to attendees for being patient for the extra time. Thank you and see you tomorrow. Have a nice day or evening. Bye.